Hello everyone, it's me Evgenii. A few words about myself. I work as a researcher in the Novosibirsk academic town. Today I would like to present the results of our work with colleagues at the 6th International Conference on Information Technology and Nanotechnology in Samara in 2020. The title of work is in front of you: Short Trace Analysis using the computer vision. The development of forensic methods and technologies for studying incident circumstances requires investigations of short traces and simulation of gas-gunpowder jet spreading. The possibility of determining the short distance by using computer vision methods on the basis of the distribution function of optical density in a digital photograph of the target with short traces is substantiated in our work. A technique for mathematical processing of digital photographs of targets is developed. The possibility of estimating the amount of soot generated by a shoot and its distribution on a target on the basis of digital photograph of the latter is theoretically and mathematically justified and experimentally validated. It is shown that the integrated optical density over each color and selected area in the target image characterize the mass of the soot material. The validity of the proposed approach is confirmed by an experiment. The possibility of identifying the patterns of the shoot product distributions on the target surface depending on the shoot distance is provided. Before I tell the mathematical description, you can see photographs of the target for general understanding of the issue to which the work is devoted. Here are presented both colored targets and targets from various white fabrics. We have developed a special installation, light box, which allows the use of various uniform LED lighting of objects that are being studied. Photos of the installation are shown on the next slide. From the left to the right you can see the frame with LEDs. Below is a photo of the installed camera, and the right are two images showing the operating modes of the installation. Also given is a graph of the spectra of the installed LEDs. Lighting of any colors has the same power thanks to customization. The installation can operate autonomously and with power supply. The slide shows the camera settings for taking photos. They must be followed at every shooting. We have tested our camera lens. As a result, it was found that the position of the lens at which the image geometry is not distorted. The height of the camera position is adjusted, so the 300 by 300 mm platform is completely placed in the field of view. Thus, the image can immediately be used to calculate the geometric parameters of the target and the patterns of soot on it. For the mathematical description of the problem, we use the following model of phenomenon under the constraints listed below. After the shot, all components of the gas-gunpowder jet move in the form of a three-dimensional cloud. Let the following conditions be satisfied. First, the gas-gunpowder jet has a limited volume, for example, a limited amount of matter exhausted in the jet form during the shot. The total amount of the matter that was not scattered and not left the jet before its impact onto the target is deposited on the target. The thickness H of the soot layer on the target surface depends on the position coordinate on the target. And the soot matter is homogeneous. Then the soot mass on the surface area is directly proportional to the product. Second, when the target is illuminated by visible light, light reflection, transmission, and absorption occur. The following relations is valid. R plus A plus T is constant. R is the reflection coefficient in terms of intensity. A is the absorption coefficient in terms of intensity. And T is the transmission coefficient in terms of intensity. It should be noted that R and T also depend on the target material. Third, The target is made of homogeneous, self-colored material with reflection and transmission coefficients. In terms of intensity, over the target surface being constant if there is no soot, no the surface. Fourth, the local absorption coefficient A is directly proportional to the soot layer thickness and hence to the amount of matter of the elementary area. Fifth, the total area of regions where the soot layer thickness is greater than that at which the entire incident radiation and absorbed in rather small. If three last conditions are satisfied, then an increase in the soot layer thickness leads to proportional reduction of the coefficients R and T. Therefore, the values of these coefficients depend on the amount of matter deposits on the area. If the distribution of R and T that is registered by digital photography depending on the method used, take the photographs in the case of diffuse reflection. If the camera total dynamic range is used and the photographs are taken to the linear segment of the transfer function of the photo matrix. In the case of photography in transmitted light, the local brightness in each pixel of the digital image is directly proportional to T, coefficient T, and depends on the soot layer thickness. The brightness is measured in grayscale level, and the maximum value depends on camera digitalization, 256 levels if the digitalization value is 8 bits per channel. The change in brightness as a function of the soot layer thickness can be written as, you can see the slide. As a result, we find the mass of soot substance. Experimental results shown on the slide. A. Monochromatic photograph of the target in transmitted light. B. Shown visualization of the concentric rings with double area selected in the target image. Picture C. The dashed curves shown the integrated optical density in the ring versus its outer radius. The solid curve shows the increment of the optical density versus the outer radius of the selected ring. Picture D shows integrated optical density in a circle versus its radius. At the left, you can see diagram of angular distribution of the integrated optical density over the target surface. The curves correspond to the angular side of the sector from bottom to top. 0.25 degrees, 0.5, 2 images, 1 degrees, 2, 5 and 10 degrees. At the right, you can see angular distribution of the integrated optical density over the target surface in the form of the catering indicatrix. The angular size of each sector is 2 degrees. The direction of the maximum optical density is shown by the solid radial line in the sector located near the angle of 270 degrees. The direction of the minimum optical density is indicated by the dashed line. Conclusion. The proposed approach and the present consideration allow one to detect and experimentally determine the soot distribution in the cross-section of the gas-gunpowder jet. A method of mathematical processing of digital photographs of target is developed. The theoretical and mathematical justification and experimental validation of the possibility of estimating the amount of soot generated by the shot and determine the soot distribution of a target on the basis of its digital photograph is developed. Thank you for your attention.